All right, let's get started. Since it's late, last session, I don't want to keep you too long. I try to be on time. My name is Christos Karamanolis. I'm a principal engineer and the chief architect for storage at VMware. And today I'm going to talk about the vSAN architecture. And my co-presenter here, who is actually sitting with you down there, is Christian Dickman, who is the tech lead, the other tech lead for the vSAN project. Before we start, I would like to actually take you first through some disclaimers. And while you are reading on this, I want to ask a few questions. How many among you have a basic idea about the vSAN, virtual SAN product? All right. So, and how many have actually tried the product in one way or another? Okay, about a quarter or so. Good. So what I'm going to do is spend the first 10 minutes or so giving a quick overview, so make sure we're all on the same page, and then start diving a little deeper into the technology, all right? Now, I'll start with some goals we set initially from the original inception of the product back in 2010-11. And actually, as a segue to that, I want to ask another question. How many of you manage vSphere, and at the same time, you also manage, in some way, storage? Wow, okay. So when I asked the same question a few years ago, I don't know, half a dozen hands that people raised. So what we definitely see is a trend where vSphere administrators, or I would say in general, IT professionals that deal with infrastructure and virtualization, increasingly they also manage their own storage. So from the very beginning, when we thought about virtual SAN, what our main goal was to develop a storage platform that was tailored to the needs of vSphere administrators, you guys. Make you be in charge of your storage needs and manage them in ways and concepts that you really understand and you're familiar with. Okay? While on that, our aim was to achieve a really compelling total cost of ownership, which consists of two parts. First, CapEx. We want really to offer very cheap, usable storage capacity, and even more important, in my opinion, really cheap performance. IOs per second is really what matters in virtualized environments. The other aspect of cost is operational expense. We really want to make this system extremely easy to manage. Actually, our mantra has been, if you know how to manage vSphere, you know how to manage vSAN. And that is, even though the system is an enterprise quality storage platform. So, and by being easy to manage, I also mean that vSAN is very well integrated with VMware products and features that you know and you use and you depend on for years, like HSay, DRS, vMotion, backup solutions, disaster recovery, VCOps, and so on and so forth. So let's see, here's the bird's eyes view of the vSAN technology. And you'll see over the duration of this presentation of how we achieve the goals we set to ourselves originally. So vSAN is software. It's software that runs on every host as part of the ESXi hypervisor. It aggregates the local storage devices, including both flash devices and magnetic disks, and makes them all appear like one pool of storage that is shared by all the hosts in the cluster and is consumed for VM storage. So it introduces a converged compute storage platform, which means that we have VMs running on the ESX host, the regular workloads, while a small slice of CPU and memory of the same host is used to serve the storage needs of those same workloads, the same VMs. Its distributed architecture is highly resilient and has no point in failure. And finally, the system, as I already mentioned, is deeply integrated with the VMware stack, which gives us very good performance, very cheap performance, and very good management experience. Virtual SAN scales out. You can grow the system by adding more servers with storage to your cluster. So your storage capacity and performance grow in tandem with as you grow your compute resources according to the needs of your applications. Actually, vSAN can even grow, scale up, if you wish, by adding more storage to existing servers, existing hosts in the cluster. And in fact, vSAN, being a software-based product, does not lock you to any specific ratios of CPU to storage or flash to magnetic disk or anything like that, like traditional hardware-based storage systems do. We provide sizing tools, and in fact, we announced last week, we had a blog about a sizing tool for vSAN that will help you to find the right ratios, the right type of hardware and characteristics for your workloads and your own needs. Now, vSAN clusters scale from a minimum of 3 hosts to a maximum of which is the vSphere cluster maximum, 32. Each host can have up to 5 flash devices and up to 35 magnetic disks. If you do the calculations with the maximum size disks that are available today, 4 terabytes, that is for an impressive 4.4 petabytes of total raw capacity across a 32-host cluster. And we have also presented, as you probably have seen, some performance numbers. 2 million IOs per second for read-only workloads, and 640,000 IOs per second for a more realistic read-write 7030 4K I/O sizes workload. But in my opinion, what is most impressive is not the absolute numbers. It's more impressive how we achieve those numbers in all practical cases using less than 10% of the CPU and the memory of the host where the vSAN runs. This is fundamental for getting really cost-efficient storage. Of course, performance and scalability are not the only factors that make a storage product really enterprise-grade. Fault tolerance is another. vSAN, with its distributed architecture, tolerates a number of different failures. Devices failures, flash and magnetic disk, controllers, hosts, networking, even including partitions. And it ensures availability of data by doing redundancy, data redundancy, at the granularity of VMs and VMDKs according to policy. So not all VMs get the same redundancy. Some more important data may have more copies of them in the cluster. Less important VMs and data, like scratch space, may have less copies, not even just 1 copy. vSAN also provides sophisticated algorithms with scheduling that implement reconstruction of data in the case of a failure of a device or host and so on, and does that reconstruction without really affecting the performance that the regular workloads, the regular applications that run on the cluster. Now, unless I've not become clear so far, let me state this explicitly. vSAN is not a virtual storage appliance, all right? vSAN software consists of a combination of user space agents and kernel modules that they run natively in the ESXi hypervisor. So we have actually moved some of the most critical modules in terms of performance, in the kernel, namely the cluster services and the data path. And we've done that because we can really improve a lot the efficiency of the resources consumed to get performance that way. And we can achieve even better latencies and timeliness for the various protocols. We have specific fine-tuned scheduling algorithms that deal with I/O, deal with isolation of different types of I/O in the cluster, data control, and so on, and can achieve the best, performance for, best bang for your buck in terms of performance. And because both the client side, the consumer of the data, and the servers of the data are all part of the same cluster, we can afford to build our own proprietary storage protocol, not NFS, not iSCSI, but our own proprietary protocol, which is much better in terms of efficiency, minimizes the number of network hops, and improves latency and user experience. Last but not least, because of this native integration, the management of vSAN is so much easier. It's so much natural, especially for vSphere administrators. And what I mean by that, there are two aspects of storage management. One is how we configure and manage the actual storage platform, the vSAN cluster in our case. We have made vSAN to be one-to-one related with vSphere cluster. vSphere clusters equals vSAN's cluster. This is a very important decision from an ease of management perspective, because a lot of the management workflows, a lot of the monitoring and control you do of your storage actually piggyback on well-known workflows that you already use today. For example, how you upgrade your cluster in a form of rolling upgrades using maintenance mode and so on. The same principles will apply here now with the storage resources of the same cluster. So managing, actually enabling vSAN is very simple. First of all, there is no software to install. The software comes with the SXI, starting with vSphere 5.5 U1. So the only thing you need to do is go to the management tab of the vSphere cluster and click a radio button. And then beyond that, the only other decision you have to make is whether you're going to let vSAN go automatically claim all those disks that don't have any other partitions that are not used, or whether you prefer to go and cherry pick the specific devices on each host you want vSAN to use. That's all. Nothing else is needed. The other aspect of management is how you provision and manage the application state, the data. In a traditional model with a typical disk array, what you have is a storage administrator, an expert, usually an expert in specific vendors' products, who goes up front and provisions and configures a number of LANs or file systems and does all those esoteric things that you probably have heard of, zoning and masking, and decides how many spindles to use and how much to casting to assign, all those things. And those LANs now are exposed, each of them as an independent data store. And now what these administrators do, actually they configure different data stores, different LANs with different configurations, different types of RAIDs, different amount of cache, so that they provide different levels of service to the applications. So now here is the vSphere admin who wants to provision the VMs and has like a number of data stores. Actually, I've been at customers' sites where they had hundreds of data stores in their infrastructure. And now the VM admin has to make a decision about which data store to provision the VM in so they get the desirable level of service from the storage. A bin packing problem that's, as some of you may know from school, it's an NP hard problem, right? So we expose all this complexity to the administrator. It's a process that is manual, involves humans. As one customer told me, I can provision a VM in minutes, but it takes a week to get my storage guys to provision the data stores. And because one has to foresee what the storage needs has for different tiers, we end up really with over-provisioning storage, wasting resources, and so on. And that was the traditional model here. Now, see how things are happening with vSAN and storage policy-based management. The VM guy, the vSphere administrator, is in the driver's seat. The guy provisions a VM, says, for this application, actually, I want this level of service, expressed in the form of policies. vSAN will take those specifications and automatically enforce them by deciding how many copies of the data to create, how to distribute them, how many spindles, where to put them. It looks into the utilization of the different resources, especially flash, which is a valuable resource, and decides where to place the data so it load balances the resources and get you better efficiency and utilization of your investment. This is automated, results in every application getting what it needs and only that, nothing less, nothing more. It is much more time efficient, and actually, you know, it's easy to change. In a traditional model, in order to change the policy of a VM, you have to storage migrate, storage vMotion, your VMs between data stores. Here, you change the one policy or two policies for a VM you want to change. For example, increase the availability or introduce striping. And vSAN will do that automatically under the covers. It will even minimize the amount of data transfers that has to happen. All right? With me so far? Here are the policies that vSAN supports in version 1. There are 3 main classes. First is capacity. You can specify actually upfront whether you want to reserve the space, the logical space of your VMDK or not, or anything in between. It can go anything from 0, which is pure thin provisioning, to 100% reservation and anything in between. The next class is availability. The main metric there is the number of failures, concurrent failures, that the administrator is willing to tolerate at any point in time. And that is interpreted into number of copies for the data in the cluster. If you say, I want to tolerate 1 failure, we create 2 copies. If you say 2 concurrent failures, we create 3 copies, okay? The other class is related to performance, and there are 2 metrics there. One of them is disk stripes. How many spindles do you want each copy of your data to be striped across? This is important for some workloads, especially like databases, where the active data set of the application may not fit in the cache tier. The other metric is reservation for flash. This is a metric that I don't expect it to be used very commonly, but especially in a very loaded system, when you have a critical application and you want to make sure it has really predictable performance, you can go and reserve the amount of flash that is used as a read cache so that you don't have any noisy neighbors really using some of that cache against this application. Because if we don't specify anything, vSAN actually fairly shares the cache between different VMs. All right. I'm not going to spend much time here. Just a quick note. There are 3 ways to provision your virtual SAN cluster hardware. Either you go and pick individual components from vSAN's hardware compatibility list. And actually, vSAN supports every server that works with ESX. And in addition to that, we have an HCL for storage components for controllers, flash, and magnetic disks. So you cherry pick the specific components you like or the ones that are appropriate for your use case, and you have a customizable architecture that is perfect for what you need. And we provide sizing tools to help you with that. The other option is to go and get from a server provider, vendor like HP, Dell, Cisco, and so on, or Supermicro. You can get a predefined and tested ready node for vSAN. You go on, you choose the SKU, and you get the server with flash, with storage controllers, with magnetic disks, everything that has all end-to-end been tested, and you know it works with vSAN. And there are different flavors. Capacity-oriented configurations, performance-oriented. For visual desk, you can get more configurations for different densities, and so on and so forth. And of course, as you probably know from yesterday's announcement, there is the third option. You can go and acquire VMware EvoRail, which is a hyper-converged virtual appliance where vSAN is the storage tier, the storage for that. All right? Okay, that was the quick overview. Let's now start diving a little deeper in a vSAN's architecture and start with the hardware. vSAN organizes storage in the form of disk groups. Each host has up to 5 disk groups. One disk group consists of 1 flash device backed by anything from 1 to 7 magnetic disks. Flash is used as the performance tier. This is where we get the majority of our IOPS out of it. Because flash devices, even though they have relatively high capacity cost, they have very cheap IOPS per second. If you do the math and divide the price of a typical flash device over the tens of thousands of IOPS you get out of it, you realize it's less than a cent per IO per second. On the other hand, magnetic disks have really cheap capacity, less than 10 cents per gigabyte these days. But they give you like 100, perhaps 150 IOPS per second, nothing, right? So if you think it from an economic point of view, IOPS are very expensive on magnetic disks. So we use magnetic disks for capacity, but the vast majority of the performance is achieved by the flash, by the performance tier, okay? So essentially we use the best from both worlds. That is the idea of this 2-tier architecture. Let's become a little more specific. Each flash device is by default configured in two partitions. 30% of it is used as a write-back buffer, and 70% is used as a read cache. Write buffer. All the write operations that come from the application, from the VM, they are replicated and go to the write buffer, which is in front of the disk where the replicas live. And the writes go to the flash, and then they are completed back to the VM. So all the writes always go first to the write buffer. They sit there for a while, and I'll explain later how we have an elevator algorithm that uses a number of heuristics to decide when and what data to destage from the write buffer to the magnetic disk. The other part is the read cache. When a block is accessed, if it is not in the flash, in the read cache part of the flash, it is brought there from the magnetic disk. And in fact, we bring an entire chunk of 1 megabytes of blocks in the vicinity of that guy, because this is a little bit now esoteric. vSAN assigns physical storage at chunks of 1 megabyte to virtual disks. So you know that every 1 megabyte chunk in your virtual disk, your VMDK, will be actually assigned to 1 megabyte of physical storage on some disk. So because workloads have a locality, spatial locality, you know that it's very common that if you read a block in some area, it's very likely to read again the same block or some of its neighbors. So we bring an entire megabyte of data into the read cache, and then from that point on, all the reads that go to those blocks are served from the flash. So with a small amount of cache, something like a flash to magnetic disk ratio of 1 to 10, you can achieve essentially all the performance is equivalent to being served from flash. Okay? That is another aspect of why vSAN is so cost effective. Magnetic disk. I'm not going to talk very much about that. I want to stress one thing, that what we do is, I'll talk a little bit about that elevator algorithm I mentioned. Magnetic disks are really bad with random operations, as you know, but they do provide decent performance throughput for sequential workloads. So that's what we try to do. Actually, we destage data from the write buffer to the magnetic disk, so that in big chunks, the elevator algorithm looks into the write buffer, looks for chunks of data that are physically proximal on a specific disk, and writes them all together. But we must not hurry doing that, because again, there is locality. It's typical, if a block is written at some point in time, it's going to be written again and again and again, multiple times within a short period of time. So as long as there is space in the write buffer, we take a little bit of a lazy approach, and we wait for this data to be potentially written multiple times before we destage the last copy to the disk. So we have only one write to the magnetic disk, which may actually capture hundreds of writes to the same blocks from the application in the write buffer. All right? Any questions on that? Okay. Let me move on. Storage controllers. So you see how much effort we have put into getting the best performance with optimal resource utilization, right? But if you don't have the right storage controller, all that work goes out of the window. So the most important metric from a controller to help you with performance is the queue depth the controller supports, the number of outstanding operations. And why that matters? Because you need to have such a lot of outstanding operations to be able to feed and utilize storage devices, especially contemporary flash devices that are very powerful. So today, in vSAN's hardware compatibility list, we support controllers that have a queue depth of at least 256 outstanding operations. And we support both pass-through controllers that allow vSAN to have direct access to the physical devices for best performance, as well as RAID controllers, in which case each physical device has to be exposed as an individual volume by the RAID controller. We do not recommend doing RAID at the controller level. Leave that to vSAN to do that per VM. granularity. Okay. Networking. There is a new class of a VM kernel network traffic dedicated to vSAN and VM kernel interface for that. vSAN supports both the old good vSuites as well as the distributed virtual suites. And in fact, if you, with a vSAN license, you get the DVS, even if you have a low-end vSphere license that does not come with DVS by itself, all right? And when we have DVS, actually we use network I/O control to provide isolation of vSAN traffic from other traffic that shares the same physical NIC. One question that comes up often is about multicast. You do need to configure multicast in your switches in the case of vSAN. vSAN makes great use of multicast to reduce substantially the control traffic in the cluster. So you need multicast. And because multicast is much easier to configure and manage with layer 2 switches, we recommend layer 2. If you are thinking about layer 3 and multicast, come and talk to us, especially this guy here, Christian, okay, who is the expert of the topic. All right, we saw how things are happening, how vSAN uses hardware. Let's now go and see how VM application data are stored in vSAN. So let me start by saying that virtual SAN is not your father's cluster file system. It is not a cluster file system. It is an object-based storage system. An object is like, think it about as a chunk of data with its encapsulated in its own metadata, which ranges anywhere from a couple of gigabytes up to, in version 1, 2 terabytes. And in the future, going to be even bigger. So this is the unit of data that vSAN manages, decides how to distribute, how to configure, how to assign resources, doing I/O scheduling, all those kind of nice features that do the enforcement of policies on a per VM basis. And why? So objects is the fundamental building block of the management model of vSAN. Each VM actually consists of a number of objects. Let's take the example here of a VM called foo, the state of which appears as a subdirectory under the vSAN data store namespace. This VM actually, first of all, consists of one object within which we create a VMFS cluster file system, vanilla cluster, in an object. To ESX, actually, objects appear like virtual volumes of some sort. So we create that VMFS file system, and we put in there all the miscellaneous files that are the metadata of the VM. The VMX file, log files, memory snapshots, and VMDK descriptor files. Now, the descriptor files, the VMDK descriptor files are those little files that contain the name of the base disk file in VMFS, if you're familiar with that. In vSAN, instead, they contain a pointer, which is the unique identifier of the object that contains the base disk of the VMDK. So here, in this case, in this example, we have two such VMDKs. Okay? Now, the administrator can specify the policy for each of these objects individually if they want. So, for example, in one of these VMDKs, for 2, I have like a scratch space, so I don't care about availability really for that or for really important performance. On the other one, however, I have a database, a critical database. So for that, I want, high redundancy. I want, failures to tolerate equal to 2, in which case vSAN will create three replicas. And even more, I ask for stripes for each replica. So I have 2 stripes. So we spread this object really, across the entire cluster. And actually those little things, those stripes in this case, the leaves of the configuration of the object are called components. So you get the idea how vSAN implements and applies this per VMDK, per VM policy enforcement, okay? So let me reiterate a little bit the advantages of this object-based approach. As you understand, as I already mentioned, they are the foundations for implementing this storage policy-based management at a fine granularity. Also, they have some other advantages. They result in better, higher availability. With traditional cluster file systems, if you are unlucky and a bunch of hosts go down and take, together some critical metadata of the file system, your whole cluster, your entire data store is hosted. Here, if a number of hosts, even if the majority of the hosts go down, but your VM has access to the majority of its data copies, of the majority of those components, the VM can still make progress. This is especially important if you have partitions of your cluster. If a VM, and actually we can even restart the VM in the right partition, I'll talk more later on. So more opportunities for your VM to continue working, better availability. The other benefit is scalability. How many of you have really seen what happens in VMFS data stores when you add more and more and more VMs in terms of scalability? Any hands here? What is the problem there? Any VMFS consumers today? Yes. Locking. A problem. It does not scale. Even though we have played some really cool tricks the last few years to do optimistic locking, still the fundamental problem there is the more VMs you have, the more host content for locking on that single data store, and scalability suffers. Here, locking is done on each object, on each VM. So you don't have all the hosts in the cluster contending for locks on the same data store. You have only the hosts that care about coordinating actions for a specific VM. When that happens, when you have a HSay failover, or when you do a migration of a VM from one host to the other. And guess what? In those cases, there are only two hosts. So you see, the more VMs you add in a vSAN cluster, locking doesn't get clogged up. It scales linearly. All right, a deep breath. Let's relax a little bit, because now we're going to go into some really interesting stuff. I'm going to talk to you about how the I/O protocols, the data path in vSAN works. And I even have three questions, and whoever asks that question correct, I have a vSAN book to give away, okay? You ready? Yes. Yes. Good. Next slide. Yes. Very good segue, because that's exactly what I'm going to talk about, the rights. I didn't pay anything to this gentleman. All right. So, how rights work, and hopefully I'll answer your question, and perhaps you can clarify if you have any additional questions. This is a simple example to make the discussion here kind of understandable, but the answer will hopefully apply to what you have specifically in mind with stripes. You have a small cluster of 3 hosts. We have a VM running on host 1. The VM has a VMDK, and the VMDK had a policy of failures to tolerate of 1, so it has 2 replicas. There is also a concept of witness. I just don't present here to keep the conversation simple, but the principles remain the same. So one quick note here, terminology-wise. The vSAN software that runs on the host where a VM is called the owner for the object of this VMDK, for example. It's essentially the owner is the coordinator of any transaction that goes on the copies and in general the components of that object. Okay, so let's go through the flow of how things work here. The guest operating system in the VM issues a write operation to the VMDK. The virtual SCSI layer of ESX handles that operation and passes it down to vSAN. vSAN, the local vSAN code, is the owner for that object, and what it does, receives the operation and clones it. Clones it as many clones as there are replicas for this, and sends now, and then it starts a two-phase commit protocol. Sends the phase 1, says, prepare this write to all the replicas. This prepare operation is sent to all the replicas, 2 here, which happen to be on hosts 1 and 2. When that prepare operation is received by vSAN on those hosts, the write operation with the data is persisted in the write buffer of the flash device, which is of the disk group where the replica resides. Okay? As long as that data is persisted on flash, that host acknowledges back to the owner, to the coordinator on the host where the VM runs. When the owner receives acknowledgements for this from all the replicas, then it safely completes the write operation all the way up to the VM. Okay? And now, you remember I said this is a two-phase commit protocol. Lazily, in the later stage, what it does, it commits this write. In fact, it commits a batch of write operations, so to minimize the traffic that goes over the network. And we can do this lazily because with the protocols we have, and I can go in more details offline with anyone who is interested in those details, we can always ensure that any transactions can always be rolled forward as long as everybody that participates has acknowledged the prepares of those transactions. And the key issue here is they have been persisted on the flash device. Okay? Now, your question is, what happens if you have lots of stripes? The protocol will be exactly the same, but instead of having 2 replicas I present here, you have, say, 3 stripes from each side. The transactions is sent to each of those stripes. So essentially what we do here, we clone twice, say we have 2 replicas, and say each replica has 3 stripes, and then each of those clones is cut in 3 parts according to the stripes you have there, and depending on where your block resides. So I'm going to chop that block of data into chunks that correspond to each of the stripes on each replica. And in fact, in vSAN we support, if necessary, under some circumstances, different number of stripes for each replica. And this is the basic idea. I can talk more with you offline after the session. So now we left those data that were written on the flash, right? The next stage is, what do we do with those writes in the flash? I talked about the staging at the very beginning, right? So we accumulate writes, and now independently in each host and each disk group, we have that elevator algorithm that goes and applies a number of different heuristics to decide what data and when to destage them from the flash, from the write buffer, to the magnetic disk. And as I said, it combines a number of criteria. It tries to create as big physically proximal chunks of data to essentially achieve sequential performance from magnetic disk, but also tries to be a bit lazy when it can, so that it can take advantage of overrides of the same blocks in the write buffer. And independently, and according to the needs and characteristics of each disk group, the elevator will destage the data to the magnetic disk. Okay? But the important thing to note here is, as long as the data has been written to the flash, already complies with the availability requirement of the user. The user asks for 2 replicas here. The moment when the write operation completed to the guest OS, the data has already been written twice and persisted twice. All right? Now, we know how writes work. Let's see how reads operate. And be prepared for that question. So the same example, 3-host cluster, VM running on host 1, 1 VMDK. The guest operating system issues a read operation to the virtual disk. vSCSI passes down to vSAN. The owner now has an important decision to make. Where do I read my data from? In this case, we happen to have a local copy of the data. That is not necessarily the case. All the copies could be even remote. vSAN does not attempt to read necessarily from the local copy of the data if one such local copy exists. And I'll explain in detail why. Instead, it tries to load balance the read load across all the replicas. And so it has an algorithm that decides, okay, this block I'm going to read from that replica. And goes there, gets back the data. If the data is in the flash, in the read cache part of the flash, is immediately returned back to the owner. If it is in the magnetic disk, it's fetched from there. You know, remember that 1 meg chunk prefetching story and all that nice stuff. Put in the SSD and then return back to the owner. The owner in turn returns back to the VM. Now, here's the question. A block of the VMDK is always read from the same replica. We don't ping-pong reading the same block from different replicas. Can somebody tell me why? Come again?
That particular block is cast
in the SSD. Yes, but it could be cast in both. You don't want. David, you're not allowed to talk. Okay. This is David Black, by the way. He's Mr. Storage. No, I should have said that from the beginning. So, sorry? Save space, yes. So between you guys, you have to figure who is going to get the book, all right? Come and talk to me. I'll have some other 3 questions, and we're going to resolve this, okay? And perhaps I'll have David here to do the resolution conflict here. So yes, the idea, to repeat here what this gentleman has said, is that I don't want the same block to be cast in 2 different, in 2 caches. It's like waste of cache capacity, and flash capacity is still expensive. I want it to be cast in only one place. And that essentially doubles or triples, depending on how many replicas I have, the capacity, the effective capacity of my read cache. All right, with me? Cool. Well, now this is the interesting part. vSAN's caching algorithms. vSAN implements a distributed, persistent cache on the flash devices across the cluster. And what we do is we cache in front on the flash device that is in front of the copies of the data. And there are many reasons we do that. One for that is because we want really to load balance the use of the flashes across the cluster. Better load balancing means better overall utilization, better bang for your buck for the most expensive storage resource you have in your system, the flash devices. The other thing is that if you had a local copy of the data, a local cache, every time the VM moves between hosts, and that happens quite often, as you know, with DRS and vMotion, then you have to migrate gigabytes or perhaps even tens of gigabytes from one host to the other. And that would affect the performance of your VM, would affect the utilization of the network resources in your cluster. And so vSAN actually, if you see, and we have actually published data, there is no performance impact whatsoever when your VM migrates from one host to another. Nothing. Now, when I say these things, there is always somebody in the audience who says, sure, but what about the latency overhead? You know, going and accessing the data from a remote host? Think about that. How many microseconds latency do you see with 10 gig network, typically? Oh, yeah, tell me a number. I'll tell you what I see and say if I agree with me. Anything from 5 microseconds to 50 microseconds. Is that roughly what you see? Microseconds, right?
It depends what kind of switch you have, what kind of
yes.
network you have. You can't minimize it, right? And if you are comparing it, you need to compare it with that case.
So, hold on, bear with me for a second. Those, and we can talk for hours about that. Now, but what I want to do is to compare that with the latencies of the devices, of flash devices. You go and look at the specs, and everybody is very excited. Oh, yeah, flash latencies are in the tens of microseconds, 60, 70 microseconds is what some specs say. Those are when you send one or a few IOs at a time to the device. Those devices have a limited internal parallelism. When you push the device to deliver thousands of tens of thousands of IOs per second, the latencies go high up. Go and look at the specs of device from Intel or from Toshiba. They will say, I will not quote, actually, why not? It's a good example. It's the Intel S3700, a very respectable device with very predictable performance. It says that with 35,000 IOs per second, they guarantee you that 90th percentile of your IOs are going to be served with a latency of up to 1 millisecond. Many other devices we see even higher than that. So you add, like, say, 10 microseconds to 1 millisecond, that is 1% difference. You know what? It's not noticeable in practice, and we have the data to prove that. I'll take a better resource utilization across my flash resource in the cluster than that 1% of latency improvement. That's how we need to think about that. And we can talk more about those for guys that are interested, understand some of the questions you may have about network configuration and so on. All right? Now, is local cache important? Yes, it is. When is it important? When the cache medium at the client side has a latency that's much lower than the network. That medium today, with today's technology, is one, memory, RAM, volatile memory, where the latencies are nanoseconds, and they're much lower than those microseconds of network latency. And that is, yes, it's very important. That's exactly why vSAN uses and works, integrates with our deduplicated in-memory read cache, CBRC, also known as view accelerator. And the important thing is to use it when a little memory, which memory is expensive, a little memory can go a long way. Without the duplicated memory cache, especially with virtual desktop workloads where there is a huge number of shared blocks among the virtual desktops, you can have a few tens of megabytes of RAM, and you can have a 90% hit ratio in that memory. vSAN works with that, supports that. Okay. Fault tolerance. I'll have to go a little faster. I got kind of carried away with this caching algorithms. vSAN tolerates disk failures, of course. And in the case of disk failures, we detect that immediately. We know when a disk fails or not. And as soon as we detect it, we declare all the object components, the data that on that disk as degraded, and we immediately start reconstructing copies of that data elsewhere in the cluster. Important thing to note here is that the load of reconstruction is shared. Both the reads, which come from the surviving copies of the data, are spread across the cluster because we distribute the data in such a way, as well as the writes, where we put the replacements across the cluster, are distributed, right? So you don't have one host, one disk group, one disk take all the load of reconstruction, as it is often the case with physical RAID. Yes?
If the disk fails, the objects that were on it, say at a fault tolerance of 2 or 1, would those objects now get copied to another disk?
Yes, that's exactly right. You read from the surviving copy. Say, we can go into the details of the various failures models, but in extreme case, if the entire disk completely collapses, we read the data from the surviving copies. Assume you had requests for some availability, say 2, and you had 2 or 3 copies. We read from the surviving copy or copies of the data, and we create a replacement copy so they're again in compliance with the availability you asked, right? And very similar with the failure of an SSD. In this case, if the flash device dies, we consider the entire disk group to have failed, and we do reconstruction immediately as soon as we detect that. We handle failures of hosts a little differently. And here's because when our clustering service, in fact, in a very timely fashion, detects that a host is not responding, we don't know with certainty, that's the physics of our universe, whether the host died or where the network got disconnected because somebody tripped over a cable or something like that, right? So, and from experience, we know that there are many of those transient hiccups with hosts. And actually, the most common reason for that is somebody is too clever with the switch configuration and screws up the configuration, realizes a couple of minutes later and fixes it, and everything is up and running again. So also because reconstructing a whole entire host worth of data is an expensive proposition. So we're a bit conservative here. We wait for a period of time. The default value is 60 minutes. You can reconfigure that. And if the host does not come up within that period of time, then I say, okay, now there is something really serious. I cannot wait any longer because I may sacrifice, I'm violating the availability policies of my users. So I need to reconstruct data and bring all those objects and VMs back into compliance. And I start reconstructing data using the same algorithms. One important comment here is that vSAN throttles the reconstruction traffic if there is high demand from the regular workloads running the VM, down to 20-25% of the traffic. On the other hand, if the workloads don't really need much, our schedule is what we call work conserving. If the workloads don't require much, don't have much demand, we're going to use as much as throughput as we can to really expedite the reconstruction. But even when we throttle, we ensure that there is a minimum progress going on so that we reconstruct the data and are back in compliance in a finite time, sooner or later. Sorry? The weakness is, actually, let me come to that in a second. because I think it will be clear there. So give me a minute or so. vSAN works natively with HSay. Actually, we really did a lot of work with HSay to work with this new generation of storage systems, which are hyper-converged. What is important here? Traditionally, HSay assumed that even if your host crashed or even host got partitioned, all those guys have access to that array out there and use the array as a tiebreaker. Here, you don't have an external entity. When your cluster gets partitioned, both your compute that HSay controls and your storage cluster gets partitioned. So there is no such thing as one data store out there. So HSay has been modified to make decisions about restarting VMs, taking into account the state of the virtual machine on certain hosts and certain partitions. And let me explain what I mean, because I see some people like scratching their heads, what I mean by an example. First, a simple case. We have a host. The HSay agents, as you are familiar with the concept, detects this host and declares that is disconnected and declares it isolated. Now, the HSay says, okay, let me see, shall I restart the VM here? Let me check its storage state on the vSAN, on the surviving host, in the vSAN cluster of the surviving host. It says here that has a majority of the data components of the VM. So it is safe to restart the VM here and actually in a host 3, okay? Why these checks are important? Look at this example. We have a partition, 4 host cluster split in 2, okay? Now, the HSay agents in each partition try to make independent decisions which are consistent, but without being able to talk to each other. What do? The HSay agents on the left side, where the VM runs, say, okay, this VM is protected, but they cannot do anything because it has minority of its components. So because the VM has only a minority of its data components, actually it freezes, and HSay eventually kills it. Now, on the other side, on the right-hand partition, the HSay agents there independently, without being able to talk to the other guy, say, okay, I know that there were some VMs that were protected, and that metadata, they have them, they're spread, they're redundant across the cluster. They know there is a VM that is actually using vSAN, but that is in detail. So HSay finds out there is a VM that needs to be HSay protected, which is probably running on the other partition, and says, okay, what should I do? Shall I start it here? It goes in vSAN and checks about whether it has a majority of its components. And in this case, it says, yes, it has a majority of the components. It can safely restart this VM in this partition, knowing well that because it has a majority of its components on the partition 2, there is no chance that another partition will have majority of the components. So it knows with certainty that this VM will be running only on this partition, so you cannot end up with a split brain situation. So to come to your question, what is the witness? Because you have, in this case, 2 replicas. If we didn't have a witness, and we had this scenario where you split in 2, there would be no safe way to determine which side to start your VM. So we have this type breaker for each object, which is the witness. It's a small, a tiny component, a tiny object that contains only metadata, no data, and acts as a tiebreaker for this kind of situations. All right? I'm going to wrap up things really quickly now. I think I have 2-3 more slides. But what I want to stress here is that hosts don't go down just because of failures. In fact, there are many valid cases where you're going to take your host off for a while for some maintenance procedure, right? Upgrade hardware, upgrade software, you name it. The maintenance mode workflow in vSphere is the most popular, the common, the building block for all those workflows that our customers use. Now, though, when you take a host off for maintenance purposes, that host may have data. So we need to do something wise about that data. You cannot really screw things up, right? So vSAN integrates with a maintenance mode management workflow and gives the user 3 options in terms of what to do with the data that reside on that host. If you know that you have enough redundancy with your data in your system, and that all your VMs will continue working normally even if that host goes away for a few minutes, you say, cool, okay, I don't want to do any data migrations. If on the other hand you want to put this host to really kick it out, what you say is do full migration of my data out of this host to the remaining of the cluster. And actually the most common option is something in between that says, well, I'm going to take this host off for a couple of hours, just migrate enough data to ensure the availability of my objects. For example, if there was some VM that had only one copy, or was a VM that had 2 copies, but in the meanwhile a disk had failed over there, and now that guy is out of compliance and is left with 1 copy, we are going to make a copy to ensure that the VM will continue operating, right? That is the option called ensure availability of your data. And this is just an example of integration of vSAN with other features, critical features in vSphere. To conclude, actually, the presentation, a storage system is not a real enterprise storage system unless it comes with tools where you can really figure out what the heck is going on. Monitor, understand what is, analyze, and God forbid, troubleshoot issues. Okay? And vSAN comes with a number of such tools. We have another session that Christian is presenting. There is the session, that session is on Thursday morning at 10:30, right? If you want to hear more about such tools, this is a very quick overview. We have vSphere UI extended to deal with vSAN cluster configuration and management, also extended to deal with policy-based management, expressing policies, and even observing not only the compliance of the VMs against those policies, but also how the VMs and their objects are distributed in the cluster. We have command line tools for the diehards who want to go to ESX CLI and do things, which ESX CLI has been extended with namespaces that do provide any imaginable control for vSAN and vSAN data. Very interestingly, we have the Ruby vSphere console, or RVC for short, which is an extendable management platform that allows you to go and perform management operations using any VC API by connecting to the VC you use for managing your clusters. And even more importantly, you can write scripts to do a lot of fancy, intelligent, high-level workflows using those APIs. And in fact, we have written a lot of those scripts that we believe that are very useful for our customers, for vSAN customers, to do many interesting and important tasks at the granularity of the entire vSAN cluster. And last but not least, the famous vSAN Observer, which is a tool that provides an unparalleled view into the internals of vSAN. You can go and look at things, how things work, and monitor or troubleshoot from a physical perspective, CPU, memory consumption, devices, both flash and magnetic disk, how they're doing in terms of IOPS, throughput, latencies, congestion, outstanding IOs, all these kind of metrics. Or you can go and look into things from a VM perspective. Your VM doesn't get the performance you thought it would take. You can go figure out what physical resources it uses. What happens with the resources? Does this VM contend with another VM? Is my system overloaded? Is some device that becomes a bottleneck even though vSAN has been doing such a great job load balancing things? What the heck is going on? Okay? And finally, I'm going to conclude with a summary of the characteristics of vSAN and its key benefits. As I said at the beginning, vSAN is a storage platform we designed from the beginning with intent to be the best storage platform for vSphere administrators. It is the software-defined storage platform for VMware. It introduces a new, radically different management model which puts the vSphere administrator in the driver's seat and provides this application-based, policy-based management so that you manage your storage based on the concepts and abstractions that matter. And it delivers a really compelling total cost of ownership, really good cost for capacity, and very good, amazing in my opinion, cost for performance. The CPU cycles per I/O that vSAN consumes are so low that cannot be met by any other product. That is the quick conclusion. I can take questions now. Yes?
Because we say it's volume store,
do you mind taking the microphone?
My question is, the VSAN is object store, which means the scalability should be very good because there's less log contention, no global namespace. But it seems like currently the VSAN can only support 32 nodes for the current version. So can you review some lessons, like what's the scalability issue you currently have in the VSAN?
Yeah, that's an interesting question. There are a number of answers to that. One reason we confine a vSAN within the size of a vSphere cluster is the obvious management benefits I described earlier. Another reason is what many customers, the feedback that many customers gave us in early stages of the product, from alpha and beta testing. They said, you know what, I'm already organizing the architecture of my hardware to be around the concept of vSphere clusters. And in fact, I organize my storage within those confinements. Specifically, there was actually one guy who was really adamant. For some reason, he thought I would go another way. He was like really angry with me until he realized that I was on the same page. He said, I do not want vSAN traffic that does this synchronous replication to go over my oversubscribed level 2 switches. Yeah, I understand. And this is really, I said, yeah, if asynchronous replication and these kind of things, fine. But I don't want my vSphere cluster to really scale across so big infrastructures that I'm going to have to change completely the architecture of my network. Do bigger clusters matter? In many use cases, perhaps they do. In that case, however, we have to go with an approach where you have topology awareness. And what I mean by that is the network topology, those constraints you have, and you make wise decisions about the placement of the data and the data transfer protocols you use between different domains in your topology. So I can elaborate further about this offline, but my point is we could push scalability further, and we may even do that in the future, but in the context of a topology awareness. Okay? Other question?
Yeah. So assuming that you have a 4-node vSAN cluster, and on node 1 you had a SQL instance running inside a VM, which was doing an OLTP kind of workload, a lot of random reads and random writes. While on node 2, you had striped data from a SQL instance, and that SQL instance was getting backed up. So a lot of sequential reads. Mm-hmm. Will a backup initiated on SQL instance 2 impact SQL instance 1?
The answer is depends on how your data is laid out.
The SQL 2 is striped. SQL 1, and one of the stripes is using the same direct attached storage as SQL 1.
So, first of all, in the case of IOs that are provided by vSAN, you are going to ensure, we're going to try our best to put the active data set of that database, the first one you mentioned, into the flash devices. And as long as that data set remains hot, are going to stay there and are not going to be destaged. On the other hand, the blocks of the database that is being backed up, very quickly we're going to see that a block is access 1, is not accessed for a while, and very quickly is going to become a candidate for eviction from the flash tier. Essentially, what would be, we have a very high churn rate in the read cache for the blocks of that sequential workload you have for the second database that is backed up at the same time.
So in a sense, you're saying that your caching policy has got intelligence to detect some kind of
sequential... Yeah, that is typical things that cache destaging algorithms do. Actually, I can disclose this. vSAN uses the ARC algorithm, which is the most sophisticated algorithm right now, which has been licensed by IBM, since IBM owns the IP there. And those algorithms are really, the best, the state of the art in achieving things with such varying behaviors of different workloads that use the caches. So yes, the answer is this is the best algorithm in detecting really quickly those not hot data and keep, evicting those that don't really matter. Yeah. Thank you. You're welcome.
Yeah, I have two questions really quick. One is compared to traditional SAN like VMax, what's the weakness? Because we all talk about the greatness. What's the weakness? That's one. Second question.
Let's ask David to comment on that. He's Mr. EMC, right? So he can comment on that.
He said VMax, I'm in trouble.
You see, that would be now I'm giving a
Okay,
fair chance to EMC to respond.
It's end of the day. We can have a debate, but I need a drink. Okay. Couple of things. One is that the 16-minute recovery time from host failure is necessary because you're dealing with servers. You will never see a corresponding 60-minute availability exposure, even on a mid-range array, let alone a VMax. Another one, and I'm not sure I understand why you did this, is I'm surprised at the consequence of single...
So actually, if you don't mind, let me respond to your responses online.
Sure. That's fair. We should do it on time. So as I said,
with a solution like vSAN, given the low cost of your hardware and the not so high premium you pay for that, you can afford to have more redundancy of your data. So you're covered for those failures you have in the system by having, in general case, higher redundancy.
Are you recommending triple mirroring all your data as a baseline?
No, it depends.
Okay,
Depends on your application, right?
Right.
You do that as a fine grain.
It depends on your policy. And in essence, if you want to achieve the availability that enterprise-grade array delivers out of vSAN, because of 60-minute timeout, you must triple mirror data that requires that availability. Now, I agree with you, not all data requires availability. So there's...
David, this is an argument not about vSAN. You realize this is an argument about hyper-converged infrastructures. So let me turn the argument around and say, with having the cluster service in ESX, we have a failure detection latency, which is orders of magnitude better than anybody else. So with that, we can really figure out very quickly what is happening with a host, right? So, but yes, in a hyper-converged infrastructure, a server is a server, and as I said, an admin may misconfigure a switch or may trip over a cable. That is
exactly, true. And we're used to this. I mean, look, SRDF provides gold standard synchronous replication. What's SRDF's usual immediate reaction to a network outage? Ignore it, hope it goes away, and during that time period, you're going to have unreplicated writes while the person misconfigures the switch, reconfigures it. So it has to do with exposure. You're exposed to an admin reconfiguring the switch, you have a 60-minute availability exposure. People don't reconfigure the inside of arrays, we don't get those 60 minutes exposure inside the arrays. Mm-hmm. So there's a difference, and I agree, some of your data clearly has lower availability requirements, and you're fine. The other ones...
If you want to have like a big iron approach, right, where everything is the hardware is fine-tuned over a period of decades to have this hardware, coupling.
I think we've hit the point of diminishing marginal returns. The next one that surprised me was the impact of single flash drive failure. Surprise that a flash drive failure takes out a whole disk group. Inside most arrays, not just ours, everybody else's, drive failures are isolated. We don't lose drives as a consequence of other drives failing.
So again, this is a consequence of the two-tiering approach for custom, right? So
I'm not saying, look, Chris, I'm not saying you're wrong. I was asked, what is the difference between level of service provided by an integrated array in which you've spent an enormous amount of available engineering? You don't control your hardware. We do. We have major advantages because of that. And what we're discussing now is some of the differences in service that you can get between people who do control the hardware and people who accept the hardware as it is and get the benefits of using the very high volume hardware on which ESX runs.
Again, if in an array, if you have even if you have replicated persistent writes, if your flash device dies, you still have to recover your data somehow, right? And you do that from the mirrored flash device, I presume in that case.
Correct. We would mirror the flash device, or if the flash is used as cache, we have ways of recovering the data, the data off the primary to cache on other devices.
And if we have a shared backplane of those disks, I assure you we're going to do the same. So stay tuned.
I mean, and I'm guessing that at some point in the future, things may change. I'm just really surprised that on a server where I've got 5 flash devices and 35 disks, if I lose a flash device, I've lost a disk.
Those are local devices. Again, they don't have a cert back.
No. It's okay. Enough.
Okay.
And having gotten up here, I was actually going to ask you a question since you called me to the mic. This one I think is a detail, is an interesting one. You had a 2+2 failure case in which the VM is running on one side of the partition and the 2 winning components are on the other side. In that particular case, you're going to restart the VM on the partition where it's not running, but you need to be absolutely positively sure the original VM is dead before HSay restarts.
Absolutely.
What are the timeouts that you're using to make sure the original VM is dead before you start the new one?
The timeouts are determined by the lock protocol we use, which is the VMFS lock protocol you know and love for that specific VM. So the current timeout for freezing that VM and eventually killing it is 16 seconds.
Okay, cool. And so in essence, what happens is it all falls down to grabbing a VMFS-like lock in vSAN, which will not be grabbed in the losing partition. At that point, the VM's dead.
Yes, exactly.
Okay,
so essentially what happens is within 16 seconds, your original VM is going to commit suicide for all practical purposes. And after 16 seconds, which is something already is in the HSay protocols, the VM will be restarted in the other partition.
Right, just want to check that, but it's absolutely necessary to make sure that the old VM is dead before you try to restart it.
And in fact, it's not even VMFS-like. As you saw in the presentation, is VMFS running in the
Actual VMFS. We use the VMFS namespace for locking, yes.
Sorry,
Let's give an opportunity to the other gentleman.
Sorry, just one more question, very quick. It's, for example, for the Oracle Rack and the Microsoft Cluster Service needed the current disks. Is vSAN support this clustering disk case? Because it requires SCSI logging.
Are you referring to SCSI reservation-based quorum? Are you referring to
SCSI reservation? SCSI reservation.
In version 1, no, we do not support SCSI reservations.
Okay, gotcha.
You know that's a matter of priorities.
Can other ESX hosts in a cluster, even if they don't have the license entitlements for vSAN, access the storage at vSAN?
Sorry, say that one more time.
Can other hosts in the cluster that don't have the license entitlements for vSAN access vSAN?
Yes.
Storage?
Yes. So what we do is if a host, you have a number of licenses, the license is driven by a number of cores, okay? And when you have a host added to the cluster and you don't have enough license credits, what we do is just do not allow that host to contribute storage to the cluster. But the host joins the vSAN cluster and can access any existing storage that is provided by other hosts in the cluster, which presumably had license credits.
So one can, in fact, create like a tier of
storage.
Oh,
no. You don't, not a good idea to cheat. Yes, that's the answer. Yep.
Okay. So Christian needled me, so I figured I'd share that comment at the mic. Obviously, you make design decisions about what you support in the first version. Persistent reservations will be important for a variety of applications, not just Oracle Rack. And I'm sure it's something you've been thinking about for future versions.
Yes, absolutely. Yes. A stress cluster is the question? Yes. So the question is, do we support stress cluster? And by that, I assume you mean metro distance stress clusters, right? In 2 different buildings, 2 different locations, the same city or something like that. No, it is not supported in version 1, but stay tuned. I would say that for sure, to give you like some hints here, in the next release, in early 2015, we are introducing the concept of a fault domain. It's more like rack awareness in this early stage. Essentially, we know of the racks. So, for example, we'll never put 2 copies of your data on the same rack, if that is your fault domain. And we're going to extend further that concept down the road to support stretched metro clusters. Yes?
What is CBRC? I saw that on one of your slides. Is it?
What was that?
CBRC?
Ah, CBRC. That is, I think, I gave a very quick description. This is, the acronym stands for Content-Based Read Cache. And it is a deduplicated in-memory read cache, which the official name of the product is View Accelerator. The feature is currently supported with virtual desktop use cases because that's the case where such a cache is most effective. And essentially what it does caching in memory, and we deduplicate that. And so essentially if you have 100 VMs on the host having one common block based on its contents, it's going to have one copy in that memory cache. And when any of those VMs tries to access that block, we run the hash, we see that we have that block, and we serve it from the memory.
How is it related to VFRC?
No relation whatsoever.
No relation.
VFRC is a flash persistent-based cache, which is placed in front of typically disk arrays to accelerate access to the disk arrays. But that is persistent cache on flash and is configured for each VMDK. There is no sharing of blocks, certainly no deduplication. It's completely different.
So when you say that you have got a persistent cache, it's always warmed up?
What cache is warmed up?
So you say that you're using the SSDs for persistent caching.
Yes.
What is persistent there?
The SSDs are persistent storage, so whenever we write some data to the cache, it is persistent. It's not in memory cache or anything like that. Also, with the read cache, if the data goes to the read cache, stays there. Even if something happens, you take your host to maintenance mode, you do something quick, you bring it back up in a few minutes, the cache will remain there, does not have to be rewarmed.
Okay, so it doesn't need to be warmed up again.
Correct, exactly.
Okay. Thank you.
One at a time, please. Yeah, go ahead. You're talking about the eviction approach. So that is a whole lecture by itself. We use, as I said, one algorithm is considered to be the most advanced caching algorithm in the industry, ARC. You can look it up and find out more details. There are a number of metrics that determine the coldness of a block and make it a candidate to be evicted. And you do that in 2 stages so that even if you have some candidates and it's from those candidates that you pick to evict, but if a block, while it is in the stage phase to be evicted, if it acts in the meanwhile, then we bring it back on. It's pretty involved algorithms, and the proof for those algorithms are very esoteric things. But it is, I hope that the industry would agree, it's the most advanced algorithm out there today. You had a question? Sorry. Yes. Trust me, in fact, we don't officially support today, but we have customers that already have systems with all flash. In the near future, we're going to have support for all flash configurations. And it's going to be, again, when we come with official support, it's still going to be a 2-tier architecture. And the idea there is we are going to have a cache tier, which is going to be a small, relatively speaking, high endurance, and therefore expensive device, will be used exclusively as a write cache and not as a write buffer. And for those who know here the small difference will understand what I mean. And then the second tier will consist of lower endurance capacity SSDs, which also will be serving the vast majority of the read operations. And again, why 2 tiers? Because we have done extensive modeling and analysis. It results in the most competitive cost model. Sorry? We can talk about that, yeah.
I have a question about when a host is disconnected from the cluster for less than an hour, how is it resynchronized again when it comes back?
Good question. So what we do is we have logs and we keep track of for all the objects that have a components on that host, we keep track of all the dirty data that have happened in the rest of the cluster. So when this guy comes up, we synchronize only those small, relatively speaking, small data of a small delta of data that have been written since the time that host got disconnected.
Thank you.
You're welcome.
Hi, so we've deployed about 50 vSAN nodes now, probably across a number of clusters. And one of the things that we've noticed is when there are network hiccups, it would be really nice if we could have an affinity rule that keeps really important guests on the same host as their disks. Is that something that's being discussed?
And why is that? Because
well, they lose access to their data.
How many copies of your data do you have?
We're keeping like 3 copies of data. But we've had problems with like UCS fabric at times. Cisco released a bug fix, and once we applied the firmware, it's been better. But from time to time, we'll see loss of access. Before that firmware fix, there was a challenge where we saw loss of access to other vSAN nodes, but the application NICs were still up. And so for really critical machines, it would be nice to set a rule that says keep the guest and 1 copy of their disks on the same host.
The important point here is that even if you have an affinity and you run your VMs when one of your copy of your data resides, you have no guarantee you're going to have a majority of your data because of the reasons I explained, right?
Right.
So it will not necessarily help you, okay?
So one clarification question for you.
Sure.
Are you saying that each individual host is getting disconnected, that the entire network is down, or are you saying that there's pockets of network connectivity where it's, you know, groups of 4 hosts have connectivity but can't talk to each other? It's really individual hosts.
Yeah, I think I'm not. I wasn't the engineer that worked on it, but I think specifically there were issues with layer 2 frame forwarding between certain hosts, and it had to do with the pinning of NICs to fabric. And once that was fixed, it was fine. But it was a kind of an odd situation that was tricky.
So if you actually had a situation where it was more about, like you had 4 servers that would have good connectivity to each other, but then wouldn't have good connectivity to another set of hosts. For example, if you use blade chassis and the chassis couldn't talk to each other. Actually, the feature that we were just talking about, the default domains, would actually be able to handle that case. So for those cases, we can actually improve the situation.
Okay, that's good. And then my other question...
Guys, let's do a favor to this gentleman back there. Thank you very much for your patience. It's like dinner time, so let's give him a chance to wrap it up here. And I can take a couple of questions offline, but you can have the microphone back.